All right, thanks everyone for coming to this session. And so you probably have seen this type of a LinkedIn in-map before, which all your connections on LinkedIn are nicely rendered, as this beautiful graph. So now imagine, how this graph would look like, if it represents the connections between all of LinkedIn's members. So in fact, it's a graph with over 500 million vertices and tens of billions of edges. So hidden inside such a massive graph are many opportunities for us to explore and extract useful and meaningful information so that we can provide better services and recommendations to our members. So in order to explore such a large-scale graph, it raises the requirement for having scalable distributed graph algorithms. Now, however, implementing the scalable distributed graph algorithms turns out to be a pretty challenging task. So for most distributed graph algorithms, in order to be scalable, it needs to be able to minimize the data transfer between vertices within the graph, as well as reduce the communication cost for sending messages back and forth between vertices. So on one hand, if we use the MapReduce-based computation engines, it will lead into inefficiencies when implementing the distributed graph algorithms due to the limited computation model it supports. So as a result, it tends to lead into more time spent on both developing as well as running the graph algorithm. So on the other hand, if we use specialized graph engines such as Giraffe or GraphX, this usually requires fitting the graph algorithms on top of some generic graph computation model, such as BSP. So while this simplifies implementing distributed graph algorithms, this could potentially also lead into missed opportunities to further optimizing the graph algorithm themselves. So facing this challenge, we started looking for an alternative. The ideal solution needs to be a generic computation engine so that we have the most flexibility when it comes to optimizing the algorithm itself. And in addition, it also needs to be performant enough, as well as providing a computation model that's beyond the simple MapReduce. So as a result, Spark turns out to be the perfect match here. So in the rest of this talk, I'm going to share our experiences building a performant and scalable distributed graph algorithm on top of Spark. And also throughout these experiences, the various advantages we discovered in Spark that make this process a lot easier in terms of helping to both ease the implementation as well as improving the performance of the algorithm. So the graph algorithm that we looked into is the random walk algorithm. So the random walk algorithm essentially simulates the behavior of a random walker that moves within a graph. So at every step, basically randomly pick a random neighboring node to move to as its next position until the termination condition is met. So the random walk algorithm actually has many variances, differing at how the random walkers determine the next position to move into within the graph. So in this example, we're actually illustrating one variance of the random walk algorithm. So the random walker will start a specific node in the graph. From this source vertex, at the beginning of every step, the random walker could either move into one of the neighboring nodes, or it could choose to restart the walk. So different from other types of random walk algorithms, this particular variance, the random restart in this algorithm is actually personalized. So that actually means when the walker chooses to restart the walk, it will actually move either back to the original source vertex or move to one of the neighboring vertex of the source vertex. So the random walk algorithm actually has many practical applications, such as personalized PageRank, as well as representation learning on top of graphs. So the variance that we illustrated in the previous slide can actually be used for calculating the personalized PageRank scores for a large-scale graph. So the personalized PageRank, or PPR, is actually a well-started graph problem. So it basically aims at identifying the important vertices in the graph that's from the perspective of every individual vertex in the graph. So for example, let's consider the graph sort of representing people's connections. Within this graph, the US president could potentially be an important node within the people connection graph. However, for some people, the US president may not be that relevant or not that important. So as a result, it does not make too much sense to actually recommend the US president to these type of people. So this difference of the personalized PageRank when comparing with the better-known PageRank algorithm makes it well-suited for generating personalized recommendations of candidate members for our members to connect to. So by starting a sufficient number of random walkers from every single vertex in the graph, we could gather enough number of random walk samples for each vertex. And thus, this also allows us to obtain the distribution of the random walkers' position using the Monte Carlo method. So from this distribution, we can further calculate the personalized PageRank scores for every vertex in the graph. So essentially, the personalized random walk algorithm does the following. Given the graph G where the algorithm is to be performed on top of, the algorithm will start in random walkers from every single vertex in the graph. So here the number of random walkers in the algorithm directly controls the size of random walk samples generated at the end of the algorithm. So in addition, this algorithm also takes parameter alpha as the probability to restart the walk. So here notice that when random walker choose to restart the walk, it is equivalent to terminating the current walker and starting a new one from the source vertex again. So we also take this restart probability as a termination condition in our algorithm. So in addition, this algorithm also takes the maximum walk length as input. So this guarantees that every single random walker will terminate after a bounded number of steps. So taking all these inputs, the algorithm essentially produces a collection of vertex pairs. And each vertex pair represents a random walk sample, indicating that a random walker starting from position S has reached position T. So by combining all those random walk samples, we can basically determine the distribution of random walker's position starting from every single vertex. And this result can be used for further processing to calculate the PPR scores. So with the algorithm's input and output defined, let's take a closer look at this distributed algorithm from the perspective of individual processors. So this is illustrated in this pseudocode. The algorithm itself is actually kind of straightforward. So it takes multiple iterations until all the random walkers are terminated. So in each iteration, an individual processor would process all the local random walkers to basically determine their next position in the move. So for each step a random walker takes, and with probability alpha, the walker itself will be terminated. Otherwise, it will move to a random neighbor until either the random neighbor is on a remote processor or the worker itself has reached the maximum walk length. So when the worker is terminated, it basically needs to be gathered as part of the final results. And from this pseudocode, it becomes quite clear that in order to implement this algorithm, the implementation itself essentially needs to address those three key operations highlighted here. First, it needs to be able to to fetch the list of all the neighboring nodes for a given vertex. So this will enable the algorithm to determine where to move the random walker for the next move. And second, the algorithm also needs to be able to tell whether a given vertex is within a local graph partition. So this will enable the algorithm to determine when to transition to the next iteration of the algorithm. And last but not least, the algorithm also needs to be able to tell how to send the local random walkers to a remote processor, so in order to start the next iteration of the algorithm. So with this understanding of the algorithm implementation, we started looking into an efficient implementation of those key operations. So the first thing we looked at is how to distribute the graph and store the partition graph inside a Spark application. So from the perspective, for the personalized random walk algorithm, representing the individual graph partitions as an adjacency list is sufficient for individual processors to determine how to move the random walkers for the next move. So the first thing we thought about in terms of representing and storing the graph is by storing it as an RDD of adjacency list. However, we quickly realized that this approach is not the most efficient way for doing this. This is due to multiple reasons. First, when we store the graph, represent the graph as a partition RDD of adjacency list, it becomes difficult to efficiently tell if a vertex is within a local graph partition. In addition, when we are loading a graph RDD partition of the graph into memory, it will incur the cost of box primitive types when storing those RDD partitions inside memory. So this also turns out to be not very memory efficient. To address these issues, we designed this custom data structure to store and represent a graph partition. So taking the example illustrated here, so basically each graph partition is represented using one efficient integer hash map plus 3 additional integer arrays. So the integer hash map basically maintains key value pairs about the vertex IDs to their local index. And using the local index, we can also fetch get the corresponding values from the offset and the length array. And using which we can easily fetch the list of neighbors for a given vertex. So illustrating this example is one graph with 4 vertices. And also the edges between them are also shown in this graph. So now let's take a look at vertex 2 and to demonstrate how this data structure can efficiently support fetching the neighbors for a given vertex. So by first fetching the local index from the efficient integer hash map, we can get the local index for the vertex we want to check its neighbors. And using the local index, we can also fetch the values from the offset and length array. And the destination integer array basically stores the list of neighbors for all the local vertices concatenated together. So using the offset and length, we can quickly jump into the destination array and fetch the entire list of neighbors for a given vertex. So this custom data structure basically support the operations for both fetching the list of neighbors for a given vertex, as well as checking whether a local vertex is within a local partition very efficiently. And in addition, since it stores data in very memory efficient format, so this custom data structure also incurs very small memory footprint. So in addition, when implementing this custom data structure, we also noticed that the Spark's multi-core computation model could actually make this even better. So we all know that Spark supports multiple cores for its executors. And usually people leverage Spark's multi-core support to increase the level of parallelism for their Spark applications. So when we're implementing the personalized random walk algorithm, we realized that Spark's multi-core support actually brings more benefits. So for the multiple cores within a Spark executor, they actually share the same JVM. Thus, by making the graph partition data structure JVM static as well as thread safe, we can easily share those graph partitions across the multiple cores on the same executor. So this enables us to partition and process the graph using all the wait cores available to the executors while sharing all the local graph partitions between tasks launched on the same executors. So this effectively means that the graph is only physically partitioned into as many parts as the number of executors we have in the application. So by requesting fewer number of executors, each with a higher number of vcores, we can keep the number of graph partitions small while still maintaining a large enough parallelism in the application to process and partition the graph. So having a fewer number of graph partitions helps to make more random walkers within the local partition. So this is especially true if we use a better graph partitioning technique to improve the number of edges that are co-located within the same graph partition. So the next thing we looked into is how to efficiently send random walkers to the correct remote vertex. So remember that in the pseudocode, we actually have 3 key operations that we want to implement. And with the custom data structure, we're able to efficiently support the first 2 operations. But the last one, which is sending vertexes between sending the random walkers between vertices, still needs to be addressed. So the algorithm itself is actually iterative and can be divided into multiple stages. So as illustrated in this diagram, each stage of the algorithm execution would terminate some random walkers based on the termination probability alpha. So the continual workers then needs to be sent to the corresponding remote vertex in order to start the next stage of the algorithm. So when all the random workers are terminated, they are aggregated together to form the final results. Taking this simple graph as an example, so this graph has 4 vertices partitioned into 2 partitions, and then which are also stored on 2 separate executors. So the random workers starting from vertex 1, on executor 1, decides to move to vertex 3 and 4. So the intermediate steps of this random worker is actually recorded as as those pairs of vertices. So this basically keeps track of the sequence of the steps the random worker has taken, and each pair represents the random worker's source position as well as current position. So now when the random worker moves to vertex 4, which is on a remote processor, now this random worker needs to be sent over to executor 2 in order to continue the algorithm. So this will basically terminate the first stage of the algorithm and further starts the next stage of the algorithm. In addition, this also raises requirement for having some routing mechanism in order to correctly send the random workers to the remote vertex, based on the random worker's current position. So when the random worker is sent over to executor 2, now the algorithm enters the next stage. So the random worker then chooses to move to vertex 2 and eventually terminate the algorithm. So one straightforward way for sending the random workers to the correct remote vertex is by joining the random worker with the graph partition dataset, based on the worker's current position. So this will always lead to the random workers to be co-located with the corresponding graph partitions after the join. However, this approach has 2 issues. So first, this will require shuffling both the graph partitions as well as the random worker dataset. So that will lead into too much data being transferred across stages. So in addition, in order to involve the graph partition in the join operation, this also means we're not able to store the graph partitions in our custom data structure. So facing these issues, we found out that Spark's zip partition operator provides the perfect solution here. So if 2 RDDs share the same partitioner, so the Spark's zip partition operator will co-locate the corresponding partitions from both RDDs. In addition, if one RDD is already pre-partitioned and stored on the executors, so the zip partition operator will essentially deliver the partition of the non-persistent RDD to the executors that having the corresponding partition from the persistent RDD. So using this behavior of the zip partition operator, we designed the routing mechanism illustrated in this example. So taking the same graph from the previous example, so where it is partitioned into 2 partitions and stored into 2 different executors. So when we are storing this partitioning the graph and storing the graph partition in the executors, we also generate a routing RDD from the graph partitions. So each element in the routing RDD basically represent a graph partition. And it also is keyed by the partition ID of the corresponding graph partitions. So by further materializing and persisting these routing RDDs on the executors, the routing RDD now essentially records the information about which graph partition is stored on which executors. So then, using this information, the routing RDD now essentially can be used as a routing table to efficiently send the random workers to the correct executors. So now by basically shuffling the random worker dataset and using the partition of the routing RDDs, Spark zip partitions operator will effectively deliver the corresponding random work partitions to the correct Spark executors, where the corresponding graph partition are stored. So this approach offers the following advantages. So first, the size of the routing RDD is actually extremely small, since it only has as many elements as the number of graph partitions. So in addition, since using this approach, we can essentially decouple the graph partitions, from being involved in the join operation. So this enables us to continue to store the graph partitions in the customized, memory-efficient data structure without involving it in the join operation itself. So this also eliminates the need, to shuffle the graph partitions across stages. So in addition, using this approach, we're able to bring fault tolerance, to this customized data structure itself. Because now this routing RDD is tightly bundled with the custom data structure itself. So whenever a Spark executor fails and we lose a graph partition, we also lose the cached routing RDDs. Now, in order to regenerate the routing RDD, it will also repopulate, the graph partitions stored in the custom data structure. So having this mechanism to efficiently and reliably send, the random walkers to the correct remote executors. So the next thing we looked into is, how to further optimize the algorithm itself. So the algorithm implementation at its current state is still not scalable, due to the fact that the algorithm would generate all random walkers in the first stage. So this would lead into too much data being shuffled, and especially in the beginning stages. So we observe that the random walkers can actually be instead incrementally started across multiple stages. So this way, we will have some random walkers started and some terminated in each stage. So when the number of new workers started in a stage and the number of terminated workers balance out, so the number of random workers that needs to be processed inside the stage is also bounded. So in fact, the number of random workers that needs to be processed is actually bounded by this formula given here, assuming that we only start P% of the random workers in each stage. So thus, by limiting the percentage of random workers started in each stage, we can control the max number of random workers we need to process in each stage. So thus, incrementally starting the random workers enable us to trade off between the max amount of random workers that need to be processed and shuffled between stages versus the total number of stages the algorithm itself needs to process. So this is further illustrated in this example in this graph. So by starting only 10% of the random workers per stage instead of starting all of them in the first stage, we actually spread out the load for processing and shuffling the random workers across the first 10 stages. So although this will lead into more stages created for the algorithm to process, and more importantly, this approach enables us to size the application properly so that we can control how much data individual stage needs to process in order to handle an arbitrarily large graph. So we further noticed that the Spark's shuffle mechanism provides additional benefits when processing the computation in such incremental fashion. So at the end of each stage, the random workers being shuffled will include both the terminated as well as the continued workers. So this would generate a set of shuffle files between each stages, having all the random workers. So the Spark shuffle file management mechanism will keep all those shuffle files until the application finishes. So this enables us to efficiently reuse those shuffle files, twice. Once between the stages, in order to send the continued random workers to the next stage, and once towards the very end, when we're aggregating all the terminated random workers to form the final results. So in addition, by leveraging the Spark external shuffle servers, we're able to further take the overhead of maintaining those shuffle data outside of the Spark executors, and thus giving more resources and more computation power to the Spark executors to actually process the algorithms. So as a result, our implementation can effectively reuse the shuffle data to combine the results across all stages by performing a single shuffle read at the end of the stage execution. So we further started the variance characteristics of this algorithm implementation with the following set of benchmarks. So the setup of this benchmark basically involves 200 executors launched on a Spark on Yarn setup, where each individual Spark executors has 10 gigabytes of memory, as well as 10 vCores. So in addition, the benchmark we did takes the entire linked-in member connection graph as the input. So for those parameters of the algorithms, we set the number of random workers to start per vertex to 500, and the restart probability set to 0.4, as well as max work length set to 20. So the first thing we looked at is how efficient this custom data structure is when comparing with if we just store the graph using RDD. So we did a benchmark by caching the graph as an RDD in memory versus storing the graph using our custom data structure. And the result shows that it actually achieves a better storage efficiency by storing the same amount of data, but in the meantime also provides a more efficient way for processing and handling the vertices in local graph partitions. So the next benchmark we did is to see how effective the incremental computation of our algorithm is in terms of dealing with graphs and with different sizes. So one thing we illustrated before is by controlling the percentage of random workers that we restart in each stage, we're able to control the maximum data that we want to shuffle, as well as the amount of data that needs to be processed within the stages. So this graph basically illustrates the effectiveness of decreasing the percentage of random workers to be processed per stage onto the size of the max amount of data that needs to be shuffled across stages, as well as the max stage execution time. So we can see that so the set of experiments we did basically has the percentage set to 20%, 10%, 5%, 4%, as well as 2%. So across those experiments, we can see that by decreasing the percentage of random workers to be processed and started in each individual stage, it can very effectively reduce the workloads that individual stage needs to process. So, but we also want to take a look at, because when we are decreasing the percentage of the random workers to process per stage, that also leads into more stages created for the algorithm needs to be processed. So we want to also take a look at the effectiveness of the increasing number of stages on the algorithm's actual runtime. So this graph basically illustrates the results of this comparison. So we can see that while the number of stages increases when we are decreasing the percentage of random workers started per stage, the total runtime does not keeps increasing. So actually there's a sweet point where the total runtime of the algorithm is minimized. So this is when the amount of data that needs to be processed per stage is not too big, and also the number of stages created by the algorithm is also not too many. So by reaching this sweet spot, we can basically choose achieve the shortest runtime for one particular size of the graph. And so to summarize, in this work, we basically from these experiences of designing and implementing a scalable and performant graph algorithm using Spark. So we learned a few things. First, Spark itself, the programming interface, enables some very powerful operations without having to program too much. The examples such as zip partitions is one such example. So basically, in order to achieve this very complete operation of sending the random workers to a remote vertex, we can simply achieve that by just using the Spark zip partition operator. So in addition, we also learned that the Spark's computation model provides many opportunities to design a sophisticated graph algorithm implementation. This plus Spark's very performant shuffle mechanism makes it a lot easier to implement efficient, scalable graph algorithms. So at the end of this talk, I'd like to also thank my collaborators in this work, who helped in terms of designing the algorithm as well as running the final benchmark. And that's all the information I have to share with everyone. Thanks.
Okay, so we have some time for questions. There is a mic in the middle for any questions.
Hey, thank you. Very interesting. I'm just curious. I have one quick question and then another a little bit more high level. The first one is the number of walkers the same size as the set of vertices you have? So you have one walker per vertex?
Yes. The number of walkers is the same across all source vertex.
Okay.
Yeah.
And then I'm just curious if you can talk a little high level between how you use the results of these random walks and how that feeds into other processes to extract recommendations of what I'm seeing on LinkedIn.
Yeah, so as mentioned in the beginning, right? So the way we're using the results of the random walk is basically to power our personalized PageRank pipelines. This is basically part of LinkedIn's POMK pipeline, to basically generating recommendations for what members can be recommended to our members to connect to, right? But the personalized PageRank is only one of the pipeline that generates such recommendations, and the results from this algorithm plus other pipelines combined together forms what powers POMK at LinkedIn.
Thank you for the talk.
Yeah.
You mentioned that one of the advantages that Spark gives is the use of, using many vCores on one executor gives great performance. So did you test the number of vCores versus your performance? Do you have any recommendations on how many vCores to use for this type of?
So the most benefits is actually coming from when we have, so assuming that the total number of cores is the same, right? By increasing the number of cores per executor, we're essentially, requesting for a smaller number of executors. So the effect of this is basically we have less physical partitions of the graph. So although the benchmark itself doesn't show that information, but the improvements coming from having more cores per executor is actually coming from now we have more random walkers that can be processed within a local graph partition. So this is where the performance improvements is coming from, right? And also, since we are running our benchmark on our shared multi-tenancy Yarn cluster, so we actually do not have too much flexibility in terms of requesting an arbitrarily high number of vCores for our Spark executors.
Yeah, what I'm referring to is that, you can increase the number of vCores up to a point. What I'm looking for is like an ideal range of number of vCores per executor where you found the best performance.
Oh, so what we discover here is as far as we're below that threshold, the more number of vCores we have, the better the performance is. And this is basically because now we have a less number of graph partitions, and more processing can be done locally without having to have a shuffle in between. Yeah.
Okay, let's give one more round of applause to Min.